Welcome to Lecture 11. This is the beginning of Exam 3 material, and it's also the beginning of our trip through chemistry land, as we are going to take the compounds that we learned how to describe and name, draw in the last set of material, and now we're going to put that together where we're actually mixing matter. So this first lecture is going to be a lot of vocabulary and a reminder about classifying chemical reactions, and then it will end with some directions for balancing chemical reactions if that's something you've never done before. And then in the next lecture we're going to get right down to writing some chemical reactions, balancing them, and so on. So the first thing we're going to talk about today is some vocabulary, the difference between elements and compounds and mixtures, the difference between physical and chemical changes, their properties, and some other aspects of solutions and so on. So I've got a nice little flowchart here that shows how matter can be classified and described according to its physical state, solid, liquid, or gas, and we have touched on that before, and according to its composition, whether it's an element, a compound, or a mixture. So all matter is made up of particles, and it is the collection of those particles that we describe as mass. Mass is just really how many particles do you have? Well, we need to be able to look at matter and think microscopically. How are the particles all the same in the substance? Then if they are exactly all the same, then we're going to call that a pure substance. So pure substance is all particles are the same. Now, particle does not mean it's just an atom. We have learned that that word is generic, so it could be a molecule or a formula unit. It could be a network of atoms, not something we've really talked about a lot. So let's just write down that pure substance is the particle that makes up the substance is the same. So all the particles are the same. So water, pure water, is a pure substance. Gold, if it has gold atoms, is a pure substance. Most of the matter that you encounter in the real world is a mixture. It is not made up of the same particles. Water that comes out of the tap is a mixture. It has other substances added to it. All right, so pure substances, constant composition, mixtures, variable composition. We can separate mixtures into pure substances using what's thought of as physical methods. We're not going to be doing any chemical reactions in order to separate them. So we can boil, and we can melt, and we can use magnets, and we can use centrifuges, and all sorts of things. We can dissolve and filter, and those are physical methods used for separating mixtures. Chemists spend a lot of their time separating mixtures. Then if you want to talk about mixtures a little bit more, there are homogeneous mixtures, which are so well, and I'm going to show you some pictures of those, very well, I'm going to call them very evenly mixed. They're so well mixed at the particle level that it looks like one thing, looks like one. Homogeneous mixtures, and we're going to talk more about that in a little bit. Looks like one substance. So sugar water, where the sugar is dissolved, it looks like pure water, but it's a mixture of sugar and water. Heterogeneous mixtures are multi-phase mixtures, poorly stirred fluids, things like most salad dressings are certainly heterogeneous mixtures. Most chemists would call, getting ahead of myself, going to talk about those in a minute, colloids. Salad dressings, potting mix, a container of gravel, those are heterogeneous. They look like more than one thing. A colloid, that's what had in my mind. Things like emulsions. Mayonnaise is an emulsion. Mayo. Blood is an emulsion. Milk is an emulsion. These substances are not evenly mixed at the particle level. They're clumpy, so that is why they're not very, you can't see through them. Many chemists regard an homogeneous mixture that you can see through as a solution. Colloids, on the other hand, you cannot see through them. Emulsions being one of those. Smokes. One of the reasons you can see smoke is that it has particles of solid in the gas, and that is why you see smoke. Clouds also have particles of solid water and other substances, and that's why you can see them. Composite materials, things especially out in nature, rocks and wood and tissues, and yeast is a biological organism. I don't know what GRP stands for. Dynamite. I mean, there are lots of plastics. They are composite materials. So these are all mixtures. Okay, mixtures where all the particles that make up the substance are not the same. Over here with pure substances, we have the chemical elements, of course, binary compounds where you have two elements, one type of strong bond, be that ionic or covalent. Polyelemental compounds, many elements, mixed types of bonding. An example of that would be ammonium phosphate. Ammonium phosphate has two polyatomic ions. So it has the ionic bond as well as the covalent bond that holds the polyatomic ion itself together. So but if you had a container of ammonium phosphate and that is all that was in that container, where every formula unit was 3 ammoniums to 1 phosphate, that would be a pure substance because all of the particles are the same. I like this little tetrahedron. I'm going to scroll here so I'll lose what I've written. I want to make it a little bit bigger. And it's about the bonding that holds materials together. Okay, so I'm going to just make it a little bit bigger for a moment so we can really see that little tetrahedron of structure bond. Oops, still can't see it. Make it a little bit bigger. There we go. So it's ionic materials, which are made up of the ionic bond, molecular materials, which are made up of molecules. Network materials are something we have not talked about. Those are things like quartz and diamond, those kinds of things. Metallic materials are made up of the metallic bond. We talked about that briefly. So you have the metallic bond, you have the ionic bond, you have the covalent bond that holds molecules together, and then you have a network types of materials where generally it's a covalent bond. Network covalent, I believe is what it says right here. It's hard to see. And those are just giant, like a fishing net of atoms held together strongly by covalent bonds. So this is a nice little figure here that reminds you of the different types of bonding. Okay, I want to, let's see, there we go. Bring that down a little bit more. Okay, so we have talked about mixtures versus pure substances and the types of bonding that holds those substances together, as a reminder. And then we have an even more detailed kind of this cube or this tetrahedron pulled apart, pure substances. So we have your network covalent, your metals, your ionic compounds, your molecular and complex salts like the ammonium phosphate, minerals, which are really, they are pure substances, but they are very complex in their chemical makeup. Glasses, that's another subcategory of a pure substance. Alloys, that's really is metals. It's almost a mixture of metals, but I guess because it's a constant composition, it's considered a pure substance. Certainly molecular substances like water, and then there are polymers like plastics and so on that we are very familiar with and don't know what we do without. All right. So that's a nice little flow chart for the different types of substances. I know that some students really haven't thought about a lot of the differences there. And really, it's the difference between pure substances and mixtures that's the most important. And then here's a picture representation of elements, of course, right here. This would be an example of most elements, not our 7 or 9 that come as molecules. This would be all your metals and so on that are made up of just pure, of atoms. So there's that, that I mentioned the little rare earth magnets, very similar it looks like that. Then we have compounds here to the right. This would be water. It's a very very recognizable molecule, but every single particle that's in there is an H2O molecule, so that's why it's a pure substance. This is not hard to see even on my computer screen. I don't know about yours. Homogeneous mixture, where things are very well mixed at the particle level, and then here's a heterogeneous mixture where, like I said before, it's kind of clumpy, and so therefore it looks like two things. So evenly mixed, where it looks like one. I cannot overemphasize enough that this is a visual thing. One looks, let me erase that. Okay. Homogeneous mixtures look like one substance because they're so evenly mixed. Heterogeneous mixtures look like two or more. You can actually see the different components of the mixture. Okay? All right, I've got some pictures here of the different types of substances. First we have elements, and instead of just one type of element like we have pictured here, the type that's made up of atoms, what I have here is an atomic element. That would be this one, where it's made up of just atoms. This one here, a reminder, when they come two at a time: hydrogen, nitrogen, oxygen, fluorine, chlorine, oxygen, I already did oxygen, sorry, chlorine, bromine, and iodine. This right here is actually iodine. Iodine is a purple solid made up of, it's a solid, so that's why it's in this arrangement. It's kind of one of this type of thing pulled apart, but there are your little I2 molecules. It goes into the gas phase really easily. The attraction between these these non-polar I2 molecules is very weak. So the solid does not remain a solid very, it's not a strongly held together solid. A lot of molecular solids are not. You'll talk more about the forces that hold particles together at the beginning actually of 132. But the nonpolar iodine molecule has very low attraction. There's no charges, so that's why it goes into the gas phase pretty easily. So these are all elements. Here are the 7 that come two at a time. The majority of the elements are made up of atoms, and this is just a picture of iodine, the solid. There are also 2 other elements that come and here they are, molecules. Phosphorus comes as a P4 molecule, and sulfur comes as an S8 molecule. And here's just a picture of a chlorine molecule. So when these elements are by themselves, okay, when I say phosphorus, I would translate that as we start to do chemical reactions. When I say phosphorus, you really should write P4. Definitely when I say chlorine, just chlorine, it's Cl2, and that goes for any of the other elements that come as molecules. So language, while we are now in chemistry land. What I have pictured here are a couple of network solids. This is actually 2 forms of carbon. This is diamond. It is a network covalent solid. held together in a network of tetrahedral carbon centers, but there's really no beginning or end to it. It's an array. This over here is graphite, which is also carbon, but the structure is different. It is in layers, so it is soft, and we are able to write with it. One of the hardest substances on Earth. This is soft enough to write with, and the difference is in the bonding. Well, this is one layer of graphite, and then quite a, the layers are stacked like it is here. And I believe that it's about 2.5. I'm not sure. I guess it's 2.5 of this distance here between the layers. Anyway, that's a pretty large distance for atoms. And so really it should be, if these two atoms are d distance apart, then the layers should also be that same distance, but they're not. It's like 2.5. So the attraction between the layers is rather weak, and therefore the layers like slide off one another, and that's how we can write with graphite. So elements come in many, in a few different varieties. This right here is quartz, another network like covalent solid. Its basic unit is SiO2, but I remember, or I hope I remembered for most of you in one of the recitation problems, it asked about the SiO2 molecule. There is no SiO2 molecule. It's a network. It's like a formula unit of these this ratio, 1 silicon to 2 oxygens. The oxygens are red here, and the silicons are black. Compounds, we have two different types of compounds, and okay, so the silicon dioxide goes with this. Down here we have our familiar sodium chloride, an ionic solid, alternating positive and negative ions. This is with the solid pulled apart. This here is more what we call a space filling model, so it's more compact. As I said earlier, if we start now to talk about mixtures, we just talked about pure substances. If we come back to mixtures, they can be homogeneous or heterogeneous depending on how it looks. So again, it's that visual clue. If you see more than one substance, it is heterogeneous. If it looks like one, then the mixture is homogeneous. By definition, mixtures are not pure substances. However, all elements and all pure compounds are pure substances. There are many students who think that water is a mixture of the elements hydrogen and oxygen, that when I write a formula for a compound that is a mixture. That is not true. Pure substances like water that are made up of molecules are, and where every molecule is the same, are not mixtures. They are chemically bonded together. So we don't call them mixtures. Those are pure substances. What I have pictured here are some very obvious heterogeneous, these first two heterogeneous mixtures. And then I just love the Kool-Aid Man. However, I couldn't find a picture of Kool-Aid. I wasn't really looking for it, but I was looking for a homogeneous mixture, picture of a homogeneous mixture. The fact that there are ice cubes in this picture kind of makes it heterogeneous, but if you ignore the ice cubes, Kool-Aid, all mixed up, or any drink like that, is homogeneous. It is very well mixed at the particle level. This glass of water here could either be tap water, which is a homogeneous mixture, or it could be pure or distilled water. You can't tell by looking at it. You would have to do maybe some tests if you didn't know. So tap water is a mixture. It's homogeneous, looks like one thing, but you can see at the particle level the other substances that are added to water are evenly mixed, and that's why it looks like one thing. All right, moving on to some more mixtures. There's some cake batter there. It looks it's clumpy, so it's kind of like a colloid, where you've got actually a colloid is an emulsion especially is a suspension of polar and nonpolar things that generally don't like each other. So you've got Usually in this kind of a mixture, you've got fats and you have water and so on, and those generally don't mix very well, but you can use agents that emulsifiers that enable those things to be mixed. Just a few more pictures to drive home these ideas. This is a pure substance. Obviously, it's an element because all of the atoms are the same. This is also an element. However, it is made up of molecules and not of atoms. So this is a molecular element. This is an atomic element. Here is obviously not an element because I see two different colors, so it is a compound, but since every single particle in the picture is the same, this is a pure substance. This, however, is not a pure substance. It's a mixture of 1, 2, 3 different substances, and I don't know if we could tell looking at it macroscopically whether that would look like one thing or not. If it looked like one, it would be heterogeneous. If it looked like two or more, it would be homogeneous if it would look like one, and if it looks like two or more, it would be heterogeneous. And the same type of thing here in this picture. So elements made up of atoms, elements made up of molecules, mixtures of all different types, or you have mixtures of elements that are made up of atoms, mixtures of elements that are made up of atoms and molecules, and so on. Okay, this right here is a compound, and it is a pure substance because all of the particles are exactly the same. This last picture right here. I don't think you can actually see my cursor when I'm moving it around. All right, a little question for you here to apply what we've just talked about. All right, so which diagram right here, these little flask diagrams, is the best representation for a mixture of hydrogen and helium? So think about what we know about the elements hydrogen and helium, what their particles would look like, and the fact that they are both gases. And pick which one you think would be the most representative of hydrogen and helium. I'm going to blow it up just a little bit. Ooh. Well, let's start to do some elimination. It cannot be B because that does not represent gases. It doesn't look like it is C. I'm going to blow this up even more. Looks like this is just an atom and an atom here in C. So we're going to knock out C and B. Really hard to tell with D. It looks to me like these particles here, this one and this one, are not made up of the same, are not the same. So the one that's obvious to me is A. I've got helium atoms and hydrogen molecules. So A is our choice because hydrogen is one of our elements that comes two at a time. So this would be hydrogen and this would be helium. So this is a mixture, a homogeneous mixture of two elements. Okay, bring that back down a little bit. Okay. All right, we're going to now move into physical and properties, and do a little space here. Whoops. Physical properties and physical changes. A lot of time is spent at the in grade schools talking about physical and chemical changes. And I think that you have to be careful with definitions. The definition that you use should apply to all situations, or it's not a good definition. So let's dive in. Physical properties and changes can be observed or done without changing the identity of a substance, which means that the particle is not changed. Okay, very important. A physical change is one in which the particle does not change. Okay, and one of the more grade school types of definitions is you can't get it back. That in general is pretty good. I can't think of an instance right now where if you, I can remember one that students would ask a lot about as we start to talk about chemical reactions and how we know we've had a chemical reaction. One of the ways we know is a gas is formed, bubbling. Well, toothpaste, brushing your teeth would come up when I would talk about this with students because there's bubbling involved. Whether or not there's a chemical change going on there, there probably is. The bubbling is just a a side product of the brushing and the substance toothpaste itself. But anyway, I deviate. The absence of those clues certainly indicates a physical change, but this right here is the best definition that I've been able to come up with over the years. The particle does not change. So, density, which I can measure density and I don't change anything, these are the biggies that students still have some trouble understanding that they are not a physical change. When we melt and boil especially, those are very energy demanding. There's a lot of energy goes in, and many students told the story many times about students going into grad school at Purdue University who were given a simple test and asked about boiling water, and 25% of the students could not answer that question correctly because they thought that the particle was changing, that when you boiled water you were actually separating the hydrogen and oxygen from one another. You are not. When you boil water, you are just turning the substance water into a gas. You have not changed the particle itself. That is a phase change, and phase changes are all physical. You can go back and forth between different types of phase changes. When you boil water and you have a top on the pot, the water condenses, goes back to the liquid state on the lid. If you were able to trap all of the water, you would find became a gas, it would come back to a liquid if the temperature were cool enough. Okay, so melting ice cube, physical change. Yeah, it's about energy and it's about states of matter, but you are not changing the particle. This here is probably a picture that was meant to go with osmosis, but one is pure water and one is sugar solution. Separating the sugar from the water would be a physical change. We will not change the particles. One is pure substance, one is a mixture. So making mixtures like the sugar solution is a physical change. It may accompany, there may be energy changes associated with that mixing, but it is still a physical change. Have you ever used one of those instant hot packs where you hit it and the separation of the water on one side and the solid on the other produced a cold mixture? Well, the substance that's in that is ammonium nitrate, which is fertilizer. Ammonium nitrate as a solid on one side, you put it in water, and this is how we would write it. We would say ammonium nitrate. Ooh, next lecture we'll be getting into really how we write it. But anyway, this AQ means dissolved in water. Well, it takes energy to do this. It takes, You've got to put energy in to separate that ammonium and nitrate from one another. The energy comes from the water. So the water gets colder. So even though the temperature has changed here in making this mixture, it's still, I have not really changed these particles. It is a physical change. So that is why the next picture is there, and that is dissolving Epsom salts as just yet another example of a physical change where I am making a mixture, and you may or may not get a temperature change. Different substances are different in that way, but either way, it is a physical change. Moving on to chemical changes and properties, you're going to change the particle, and that's what we're going to spend most of the rest of this exam material talking about. However, at the very end, before we head out of the material, we will come back to mixture solutions. Substances that are flammable will burn, exhibit the chemical property of flammability when the chemical change, burning, occurs. So chemical properties are the things you see as a result of a chemical change. When a copper on the Statue of Liberty or on a roof becomes green, the color change is because of the chemical change. The chemical property of copper turning green is just associated with that chemical change. Okay, so changing particles is the definition of a chemical change. So here I have some pictures of chemical changes. Just about all cooking is a chemical change. You certainly can't get that fried egg back to a raw egg status, but I have changed the particles. The proteins and the fats in the egg are being solidified, changed by the heat. Burning is always a chemical change. Lots of energy given off. I just said, however, that energy changes can accompany physical changes. So a temperature change by itself is not always a rock solid indicator of a chemical change. But burning with the heat, the light, gases being formed, which is actually what's burning is the gases, is always a chemical change. Roasting that marshmallow over, well, I don't ever do it over a candle, but over a campfire or whatever, is cooking. You are changing the chemical makeup of the marshmallow. That's a chemical change. I put this picture of a frying pan, this cast iron frying pan here on purpose because I just can't stand it when people don't take care of their cast iron. But it's a rusty cast iron pot pan, fry skillet. And I just hate to see that. You must take care of your cast iron, rusty cast iron skillet. The rust is a chemical change. Season it so that doesn't happen. What we are seeing here is an example of what we're going to talk about starting with our next lecture. Here you have one solution, which means it is a compound dissolved in water, like that ammonium nitrate I talked about earlier. Okay, so it's aqueous. Okay, so it's clear. I could give you some ideas of what it probably is. And in the little dish here, I have another solution, a different substance dissolved in water. Okay, but when they hit, they form a chemical change. So I'm seeing the new solid being formed, the color change. Those are my indicators. This type of reaction is a precipitation reaction. And we will talk about those in the very next lecture. So this is definitely a chemical change. I'm taking one mixture and another, putting them together, and they form a new substance, a new particle. The particles are changing, so that is a chemical change. All right, so if the particle is changing, what is going on here is that bonds are breaking and new bonds are forming. So if particles change, I need to break some bonds and I need to form some new bonds. Versus what happens in a physical change, you can change the spaces between particles, for instance, when you go from a liquid to a gas, but you have not broken the bonds or made any new ones. You can change the speed because you're heating them up or cooling them down. There's a big difference between breaking bonds and making new ones and just changing the spaces between them or speeding them up. Okay, so the physical change of water into ice, okay, the freezing, all I'm doing is changing the spaces. In fact, for water, that's different from most other substances. Those spaces actually get a little farther apart, and that's why ice floats on water. But if I take water and I change it into hydrogen peroxide, which we have done Lewis dot structures for, then that's a chemical change. The particle has changed. So here it's showing in this picture, this one right here, that what I'm doing when I take ice, so this is a picture of ice, okay, it's a really different kind of a structure, and what I'm doing is I am disrupting the force of attraction between the molecules, which is a hydrogen bond, when I melt ice into water. And therefore I have changed the spaces between them, and I have changed their speed, but I have not changed the particles themselves. You see that these particles are exactly the same as these particles. So we've just looked at particles. We looked at a few pictures that were very obvious, okay, for chemical changes, but how do we know what to look for in the real world? Your text lists 5 clues on page 208 with pictures very nicely. Color changes, formation of a gas, formation of a solid, emission of light, and emission of absorption or heat. I contend that since light and heat are both forms of energy, we can combine those two. And if you see something new phase of matter, like a gas or a solid, okay, I say we can combine those two as well to give us 3 visual clues. Color change, new state of matter that wasn't there before, or a change in energy. All right? So those are our indicators, and I've already, talked about them as I went through the examples of a physical change. I'm sorry, chemical change. Chemical. That tells us when we see these things, not this one necessarily by itself, because that does accompany mixtures, but definitely these other things, combined with this, yes, tells us that those particles are being changed. All right, we're going to move on to talking about balancing chemical reactions, and I've got a couple of tips for you. And then I'm going to show you some programs that you can go to on your own and practice. A couple of things that students do, and let's make sure that we understand some of the vocab here. First and foremost, you can only change coefficients. Coefficients are these numbers in front. Subscripts are the little numbers that we were using when we put the formulas together in the last material. So when students balance chemical reactions, sometimes they want to change the subscripts. You cannot do that. When you start writing your own chemical reactions, so let me just write this one off to the side. When you write your own chemical reactions, students want to do this. They want to carry those subscripts over. No, 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 because you are making a new particle. Okay, so what happens over here depends on what type of reaction it is. Looks to me like we are taking a molecule like hydrogen and putting it with, I don't know, let's say it's oxygen and magnesium, something like that. That would be the type of reaction that we see here. Magnesium is made up of atoms. Oxygen is diatomic. When I put magnesium and oxygen together, Think about the charges, because this is a metal and a non-metal. Okay, so we go back, that never goes away. So magnesium is +2 and oxygen is -2. So MgO would be the right formula for magnesium oxide, but in order to balance this chemical reaction, I need to put coefficients in front. So a 2 there and a 2 here would balance the chemical reaction. Okay. The substances that are on the left of the arrow are called reactants. Okay. And the substances that are on the right of the arrow are called products. Okay. Always save oxygens for last. All right. That's a tip. They are often in several compounds, and they can be a problem. You want the lowest combination of coefficients. So you don't want something like, let me just take this example here. You don't want to end up with this. It's not exactly wrong. It's just what we call overbalanced. And when you try these little programs that I'm about to show you, this would be judged incorrect, because you need to divide all those coefficients by 2. So we're going to go to this ChemBalancer program that I've used a lot, and it's going to help you get started if you've never done this before. If you need more practice, it's an excellent place to start. So we're going to go to this link right here. Okay. And what you want to do is you want to start with this one first, then come back and do this one, and then do this one. Let me show you how it works. Just do a few with you, and then I will leave that to your practice, on your own. So let's go ahead and click on it. So we say start game. Let me take this window over a little bit. Okay, the thing that I like about this program is that you get pictures. And I think that helps students with the balancing if they're not familiar with it. So in order to get pictures, put a 1 in each box. Okay? So underneath you get some like little Lewis dot things without the dots. I wish that they put the arrow in the pictures, but they don't, so you'll have to do that yourself. Let me show you what I'm talking about. I wish that there was an arrow here, okay, but there's not. So what you're looking at is I see 1 iron on this side, I see 1 iron on this side, so 1s in all of the boxes looks like it is going to balance the reaction for us. So then you click on, then you click on the balanced, and it will tell you whether you're right or not, and leads you to another correct, and then it gives you some trivia. Latin ferrum means iron, so that's where the symbol comes from, so on and so forth. Okay, so here's your next one. Put 1s in each box and you will get your pictures. You can just do that by tabbing. Again, the arrow is not there in the pictures. You can draw it in mentally. Okay, so on one side of the arrow I see 2 hydrogens on this side, 2 hydrogens here, but I only see 1 here. I see 2 chlorines on this side, but I only see 1 here. So I am going to have to change my coefficient in front of HCl to 2, and then I get the 2 hydrogens that I need and the 2 chlorines, and then click balanced, and it tells you that you're correct, and then it leaves you to another one. Here's that example we just talked about. So what happens as you finish, you can go back to the ChemBalancer, fun-based learning screen, or chemistry. Just click on this. When you're done, click on chemistry, and then you can go back and then do review and brain boggle. Gradually, as you get at the end of review and brain boggle, they will wean you off of the pictures, and they do get some, they do get kind of tough. I am going to show you in the notes, since we're not too long at this point, about one trick that will be very helpful. So let me go ahead and go back to the notes. There is another link here, and I want to show you that one really quick. It's a little different, but it is endless in the examples. And so you say, now you don't get any pictures. New reaction, and then you go ahead and get started. Let's see, will this one do? Let me do this one really quick. So I see I have 2 carbons. Remember, do oxygens last. Let me see if this one isn't the trick. 2 carbons, hydrogens. I have 3 on this side. Right now I have 3 on this side. 2 and 1 is 3. 1 chlorine, 1 chlorine. So I have 4 oxygens on the right, plus 1 is 5. Yes, this is the trick. All right, so this is the deal. On this side, I have 1 oxygen here, and then 2 times 2, 4 oxygens here. So 5 oxygens altogether. But over here, I have O2. This happens quite a bit where you get this odd number of oxygens. So this is what you're going to do. You're going to put a 5, the odd number, in front of oxygen. Then multiply all the other coefficients by 2. So 2, this one here becomes, I'm going to have to do this. I'm going to draw them in, and then I'm going to click out and put them in. But this is what you're doing, because this is what you're really doing. I needed 5 oxygens on this side. If I put 5 halves in front of O2, I would get 5. But I don't want the half. So what I'm doing is I'm multiplying all of the coefficients by 2, which is why I ended up with 5 here. And then all the other coefficients are 2. So let me go ahead and do it for real and show you that that works. Okay. So it was 2, tab, 5, tab, 4, tab 2, tab 2. And then you say, check answer, and it's correct, and you say new reaction, you get another one. Okay? Give those a try, and that would, between the chem balancer and this one, that should give you all of the chemical balancing practice you need. I'm going to put up a worksheet in order to give you some more practice if you'd like to do that. All right, we are going to end this lecture by talking about types of chemical reactions. This book and many college level books deviate a little bit from the classification system that you learned. It's there, don't worry, in high school. And that was the following: synthesis, combustion, displacement, double displacement. And I am missing one, decomposition, in that list. Excuse me, but it's down here. There's nothing wrong with that. Notice that I myself have interchangeably used the word displacement and replacement. Different books use different words, so I kind of use them both. We are going to focus on double replacement reactions first. In the next material, we're going to start with those. And as these encompass precipitation reactions and acid-base reactions. So that's the first type of reaction that we are really going to focus on. And then there's a new type of reaction that we're going to talk about in this course, and that is oxidation and reduction reactions. So this older type of, or this other type of classification system that you may have learned before is fine, and we are still going to use it. However, this book introduces the idea that really there are only 2 types. Those in which oxidation numbers change, and that's called redox, and those in which they do not, and those are all double replacement or displacement reactions. So that's a more general classification system, a little more on what is actually happening with the electrons in chemical reactions versus looking at what happens with the particles. So I'm going to go through the one that you've probably encountered before to finish the lecture up. Okay, so I've got a little thing here where synthesis reactions, metathesis is another word that's used by some chemists, and that is when you take 2 different substances, they could be elements, and you make one. So 2 becomes 1. Decomposition is the opposite of synthesis, and that is when one compound, it has to be a compound, becomes two or more substances. Those two or more substances can be elements or compounds. So one compound could break down into an element in a compound, or two elements, or two elements. Same thing up here with synthesis. You could start off with two elements and make a compound, or you could have an element and a compound makes, and it doesn't necessarily, it does not have to be two elements make a compound. It's two becomes one becomes two or more in decomposition. Okay? Single replacement. I always say it's like you go alone to the dance, and you get to go home with somebody else's date. And the person who was with that person has to go home alone. So this one is always compound plus element. You make a new compound, and one of the elements that was in that compound before is now alone. It's now the element. Double replacement, the one that we're going to talk about first, is two compounds. Always two compounds making two compounds. Okay, so that's how they're pretty easy to recognize. All right. Our last type is combustion. It can be an element or a compound, but oxygen always has to be here as a reactant. Oxygen, the element, and you make an oxide. So this reaction that we talked about before, magnesium plus oxygen to make magnesium oxide, that is a combustion reaction. This particular one involves some bright burning. Many combustion reactions do involve burning. Or another very common combustion reaction is when I take a compound that has carbon, hydrogen, and it could contain oxygen, and combine it again with oxygen as an element. I always produce carbon dioxide in water. Always. Okay? Always. You need to know this one. Know these products, because it's not that hard. When you take a compound that contains carbon and hydrogen, or it could contain oxygen as well, like gasoline, and you burn it in the presence of oxygen, combustion, you make CO2 and water. All right, and then I'm going to follow this one link here, and we'll be done. So let's see what this is. Well, I think it was probably an AP chemistry thing, perhaps? No? Well, I'm going to have to retire that link. So that concludes our lecture 11.